vectors. Okay, it's just some mathematical background. Okay, so you can be having 4 tensors as well. Okay, let's say, suppose, okay, what we did, we had this kind of quantity. Okay, let's say some u, the velocity for vector ui, it's having 4 components. Okay, so like this in u0 and ui, or any other quantity, let's say a, so it's having how many components? 4 components. In vector, so I should write here. So and you are having the vector. Clear? Now, what is the transformation rule here? So the transformation rule was, you are having some quantity ai, so it transforms like this: li prime, j, and a. So this is how we define it as a 4 vector. L is a matrix that specifies us the particular transformation. Those transformation here are the Lorentz transformation. Clear? Now you are having only one index here. Now if you are having a quantity, okay, so let's write this kind of quantity. Let's say you are having a I, okay, and something bj. Okay, I am having 2 vectors, 4 vectors, ai and bj. Clear? 2 distinct indices are here. Okay, so let me call this quantity as something Cij. Okay, so that means I have constructed a quantity which is having 2 free indices. Okay, now let's check how it transforms. Now, if each index transforms in the same way as this thing, let's say, okay, so let me write it here. So I am having this Cij like this thing, ai, bj. Okay, so now let's look at the transformation rule. So what it means, Cij, so in the primate coordinate system, it is something ai in the primate coordinate system, bj in the primate coordinate system. Okay, now ai transforms how? So you are having ai, li, let's write k, ak. Clear? For 1, so for one of the index I am putting like this thing. For b, so what I will put? Some L is a matrix, Lorentz transformation matrix. Let's write it as B Lj prime. Let's write it M. Some B. Clear? So what is now the transformation rule? So you are having Li prime K, okay, Lj prime M, then you are having this AK Bm. So, or in other words, you can write it like this thing: Li prime K, okay, Lj prime M, and this is your CKM. So now each index transforms in the same way as the 4 vector is transformed. Clear? So this I call as, so how many free indices are here? 2 free indices. समझ आया? I and j are the free indices, k and m are the dummy indices. So this quantity I call as a tensor of rank 2. Okay, but here I will call it as a 4 tensor. I will not be here I am not defining tensor in a general way. How to define it? Okay, as a general transformation. Here I restrict myself to only a coordinate to a Lorentz transformation. In general, there will be actually a well-defined coordinate transformation that will define actually a tensor. Clear? So we will call it as simply as a 4 tensor or simple tensor of rank 2. Clear? समझ आया? Any problem? Okay, so this tensor can be symmetric as well. Okay, so this can be both contravariant as well as covariant. Contravariant means, so you will be having indices up, and covariant means indices down. Forget about contravariant and covariant. Just know there exists actually certain quantities for which each index transforms in the same way as the 4 vector is transforming. Clear? We call those quantities as tensors. Okay? Okay, so these can be symmetric as well as antisymmetric. Symmetric means, so I will just give a, so if you are having a symmetric tensor, so it is something Cji. So we call it as symmetric. Symmetric under exchange of indices I and j. Okay, so if you interchange I and j, so if the quantity remains the same thing, okay, Cij is same thing Cji, so we call it as a symmetric. Similarly, you can be having an anti-symmetric, you interchange it like this. So if it gives you, so we call it as an anti-symmetric rank 2 tensor. Clear? So the well-known example we have already studied, so that is Fij, the electromagnetic field tensor. So what is that? Partial I Aj minus partial J A. So this is the field tensor which is antisymmetric. Clear? Clear? Okay, so for symmetric tensor, if you know the energy momentum tensor, we have already described in the electrodynamics course. So that is an example of symmetric rank 2 tensor. Clear? Okay, so this is a general idea kind of thing. Okay, so now let's move ahead. So this you should know. Here it is. Okay, so now let's go to our this 4 velocity. Again, 4 velocity. Okay, so how I define the 4 velocity? Now let's look at it. Try to figure out the components. Suppose if you are having a particle that's moving along a trajectory, okay, along a world line, let's say. So at each instant of time, so this is a parameterized curve. I will not say it's always a parameterized curve, and this curve is parameterized by the proper time. That is why it is called a world line. Okay. So at each instant of time, okay. So you define a tangent. Okay. So these are specified the coordinates chi I tau. Sorry, xi tau. Okay. Xi is the 4 vector which specifies you the coordinate of the particle. Clear? So now draw a tangent at each point. Okay. So it will be like this thing. So this tangent I call as ui. Okay. So now I define my 4 velocity vector as dxi by d tau. So this is a function of tau. Clear? So this is how we define the 4 velocity vector. Okay. So now let's figure out the components. Okay. So let me take I is equal to 0. So what that will be? dx0 by d tau. Okay. So what is x0? Okay, x0 is c dt by d tau. So you can call this as a function of tau. This also the function of tau. Now what is the relation between proper time and the coordinate time? This t is actually the coordinate. Clear? So it is the coordinate specified by at each point by this observer. समझ जाओ? Okay. So what is the relation between t and tau? So we have like this thing, tau d tau. We know it is dt root of 1 minus v square by c square. Okay. So now tell me what it will be. It will be c dt by d tau. It will be 1 divided by root of 1 minus v square by c square. This is the zeroth component. Okay? Any problem? Okay, so now let's go to the other components. Okay, so let me take now u alpha. Okay, alpha is what? Alpha is 1, 2, 3. That means special components. Okay. So what is that equal to? Now tell me. So it will be simply dx alpha, that is the function of tau, by d tau. Okay? Samashama? What is x alpha? It's actually the coordinate x, y and z. Okay, so I need actually the differentiation of the coordinate with respect to the coordinate time now. So I will convert this d tau into the coordinate time. Got it? Then that defines actually a valid quantity. Huh? Okay, so I will write it as dx alpha tau. Okay, by what is d tau? D tau is dt. Okay, root of 1 minus v square by c square. So this I write 1 by root of 1 minus v square by c square. So dx by dt is now velocity. Okay, velocity of the particle. Clear? 3 velocity. Yeah? So I will write it as simply u alpha. Sorry, I will write it as a v alpha. Let's write it as v alpha. Or in other words, I will write this u vector like this thing, v vector divided by root of 1 minus v square by c square. Clear? Any problem? So now what are our components? Okay, so what are the components of the 4 velocity vector?
Sir,
Yes.
sir, I have a confusion.
Yes.
Sir, tangent is actually the slope.
Uh-huh.
Sir, but no, it's t from that side and x.
No, it's not like. So this is okay. How you define now the velocity? So when you define certain quantity, you at least need 2 observers. Okay, so you are having a moving observer and a person sitting at rest. Okay, so the person sitting at rest specifies the coordinates of that very person.
Sir, actually, I mean, shouldn't it be the
No, it's not like that. So this is simply a schematic view. So you are saying this tangent should be like this triangle.
So no, sir, I mean tangent. Sir, I mean velocity should be x by t, but that is not the tangent. That is the reciprocal of tangent.
Where is that? You see this
dt by dx.
huh?
She
No,
means to
it's
say-
not.
She means to say that time axis is vertical.
Oh no, you don't see. Don't look it from this very perspective. Suppose I am giving a curve, simple curve. Okay, so let me take a simple curve. So and I want you to draw a tangent. What you will do? You will draw a straight line at that point. Clear? And how that you specify? Let's say at this very point you want to draw a tangent. What you will do? So it will be like this thing, a line. So now this tangent for the frame of reference there. So for a co-moving frame, okay. So what that will be equal to? So what is the coordinate divided by the proper time? Got it? So this axis only specifies you the coordinates. Just feel the difference here. So this x and t, this very axis. So when we are talking about, if you remember the time dilation phenomena, so I have always specified an observer which is moving, okay, with his own clock, okay, and you are measuring at rest, and you are saying you are giving it the coordinate time. That means you are measuring that very clock. समझ रहे हो? Similarly, you are having here the same way. The particle goes with the velocity, 4 velocity, okay? So it is the proper velocity of the particle itself in its co-moving frame. I mean in this very frame of reference. But you want to measure it from your perspective, the ground observer, let's say. Okay, what that will assign? That will assign coordinate straight. समझ रहे हो? So this picture depicts that kind of thing. It's simply the coordinate axis you are giving to the observer here. Now if you look at this xi tau, why I have put it as a function of tau? Since xi will be specifying the coordinates, but those coordinates will be dependent on what? How you choose the curve, how you parameterize the curve. So that is the proper time. Clear? Any confusion? Okay, don't look at the diagram. Diagrams are sometimes misleading. Okay? Clear? Okay. So now what we have got. So what we have got. So ui therefore I can write as. Okay, so what is this factor? 1 divided by root of v, so it is gamma. So I'll write it as c times gamma. Then I can write the another v vector. So this I can, let's say, write u0 and vector u. So what is that? Gamma times. Clear? So now let's take this very product ui. Now let's check the inner product or the norm of this very vector. So this is simply the norm, okay, length of the velocity vector. Now let's check it. So what is that equal to? So it is equal to u0 u0 plus v dot समझ आओ? So or you can say, let me write directly instead of u dot. Okay, u0 and then u0, u and u. So what is u0? So it will be simply like this thing, u0 multiplied by u0, because you take this u0 upper, so that will give you the minus sign. So it is u dot. Clear? So what is u0 u0? It's minus c square gamma square. Okay, so it's minus c square gamma square plus what is u dot u? It's gamma square v square. Clear? So now let's calculate it. So how much is that? Okay, so how much is this equal to? So you take gamma square out with minus c square. Okay, so what remains here? 1 minus v square by c square. Gamma square is 1 divided by 1 minus v square. So gamma square into this is equal to 1. So it is simply equal to minus c square. So that means your velocity vector is time-like. समझ रहे हो? Got it? So it always stays inside the light cone. Clear? Any question? So suppose if you are having, let's say, the particle is moving along this very trajectory. So draw at each instant of time. Okay, draw a light cone like this thing. Clear? So draw a light cone at each instant of time, kind of this thing. Huh? So at since this line represents the set of events, at every point you describe an event. Clear? At every point you draw a cone. Clear? With the this very vertex at that very point. So that means this very velocity vector, let's say at that point you draw a tangent, it will be always where? Inside this light cone. Clear? So because all the time like events are where? Within the light cone. Clear? Okay. So now let's write the acceleration. For acceleration I should say. So this we define as, let's say, AI as d2 xi tau double derivative with respect to this. Clear? So simple. I'm just doing the simple math. Okay. So what it gives me? So this I can write as something a0 and acceleration vector. Clear? So now let's compute the components. So, or I can write this thing AI as, so it is simply dui by d tau. Clear? Simply, dx by d tau is velocity, du by d tau is what? Acceleration. Okay? Got it? So you can now calculate the components. What will be a0 and what will be a. So that will be as an assignment. Simple differentiation. Okay, what you need to do, you need to convert this tau into t, coordinate time. Clear? So just make sure you do it correctly. Okay. So now let's look at this very relation. You are having this ui, that's actually equal to minus c square. Okay. So now let's differentiate this very relation with respect to proper time. Clear? So I can differentiate it dui by d tau, so it will be ui plus ui dui by d tau, that's equal to 0 because this is a constant. Clear? Okay, so now these are actually the same quantities. You can, okay, so let's say in this very, sorry, so it's I is time. So you can raise this index up and lower down this thing. So what I mean by that, so you are having ui that is same as what? ui. Clear? Whether you raise one in, okay, once you raise one, the indices which are contracted, that means summed over indices. So if you raise one and then lower the other one. Clear? Samajh? Okay. So that means these two terms are same. So what it gives me? What is this thing du by d? So this is the acceleration. It means ui, okay. So let me write it this way. So you are having this ui and ai, that's equal to. So what it means? So acceleration vector is always what? Orthogonal to velocity vector. This is actually the dot product, so this is equal to 0. So it means, so now we have seen ui is actually a time-like vector. Yesterday, when we were describing the surfaces, okay. So what we have seen, if you are having a time-like surface, so it means the normal to that surface is what? Space-like. Okay. So if you choose now velocity to be time-like, then the acceleration vector is where? It's a space-like vector. Clear? So in other words, if you draw like this thing, suppose if you are having, let me draw this world. Okay. So let's say this is your velocity vector ui. So then you are having this as the acceleration. Okay. समझ आओ? Okay. Clear? Now let's look the application of this. This has an important application. Okay. So we will see an implication of this very relation in a moment. Okay. We'll look at the Newton's law. Okay, Newton's second law. Can we generalize it directly? Does it hold in the theory of relativity as? We are not doing general theory, we are just doing special theory of relativity. Okay, so whether Newton's law can be taken directly to the special theory of relativity or not. Okay, so that will be actually, this relation will give us the idea, shall we generalize it or not. Okay, so now let's look at. Any question till now? Okay, so let me take. So what is our Newton's law? So Newton's law is mass times acceleration. It is something gradient of the potential in a conservative field. So phi is some potential. Okay, so if you write it in this way, so this gives you the Newton's law, force law in the conservative field. Clear? Okay, because you are specifying F is equal to minus gradient of phi. So or I can write it in the notation. Let's say M A alpha. Okay, alpha means 1, 2, 3. So this I can write as minus partial alpha phi. So alpha is how much? 1, 2. Clear? Any question? Okay. So now we can say, we can say, we can generalize, since this holds only for special components. Clear? There is no temporal component. Let's generalize this to including the temporal component. Okay, we can say that we can write this law as in this form: ai as minus partial I. Okay, so I is 0, 1, 2. So that means I simply generalize it directly to what? 4 component equation. समझ आओ? So that means what I am saying, let's propose this as a relativistic generalization of the Newton's second law. Clear? Any question? Okay, so now let's check whether this is true or not. Whether this can be a generalized equation or not. Okay, so the previous equation will help us. So how? So let's take a dot product with ui. Okay, so take dot product with ui. Okay, so what it means? So it means, so m ui ai, that's equal to minus ui partial I phi. Clear? What is this very side? So this object is equal to, okay, so what it gives me? So it gives me ui partial I phi, that's equal to 0. Okay, समझ आओ? So now let's check what exactly this relation means. Okay, so I can write this thing. So let's write d phi by d tau. Clear? So let's write this very quantity, I mean total derivative with respect to the proper time. How I can write it like this thing? Anybody? So I can write it partial phi by, okay, let's say partial xi, then I can write partial xi by partial. Can I write it? Can I write it? Simple chain rule. Huh? Okay, so what this object is? So this object is your 4 velocity vector. Clear? So it is ui. What this object is? Partial I. Okay? समझ आया? So now what this object is? It is the same thing. Okay? So this means it's equal to 0. So use it this way. What it means? So if you are going, since your world line is governed by this tau, okay, the proper time, that means this potential has to be constant. So as the particle moves along the world line, what it means? So potential should always remain, but that's not true. So when the particle moves, the potential, it's not necessary, potential always changes. Clear? So it means you are having, so the implication of generalization of this law as such implies always you are moving along a constant to potential, or that means along the world line potential should always remain constant. That is not consistent. Clear? So Samashiman, got it? So have you got the idea? So that means this generalization is not valid. Okay? Samashiman? So what it means? So since in this very case, I have taken the force as independent of the velocity. It only depends on the coordinate in the conservative field. Is it clear? So this means, this analysis means the force is not only dependent on the coordinates, but it should also depend on the velocities. Clear? So when you try to generalize the force in the relativity, I mean simple relativist mechanics, so you need to define actually it as a velocity dependent force. It should depend on the velocities. So that should be actually clear from when we define the 4 vector A. So it depends on the velocity, that gamma factor. Clear? Samajh? That gamma factor contains the velocity. When you try to calculate the force, you will see there will be the force in the longitudinal direction is something, and force in the transverse direction is different. Clear? Samajh? Have you done this kind of exercise? Okay, just look at the visor and calculate the force. Huh? So it is defined there. But my idea, the point here was that we cannot generalize this thing directly. Okay? So this is not valid in the relativist mechanics. Clear? Okay? Any question? Any question? So now let's look at motion under constant acceleration. Or uniform acceleration. Okay? I should use uniform, but let's use constant. Okay? So let's consider the Newtonian mechanics. So in Newtonian mechanics, so which is the equation that will give you the constant acceleration? So you are having this dv by dt, that's equal to constant. Clear? Is it true? So what it means? So this simply means the constant acceleration. Now if I have to calculate the velocity from here, so you call this constant as the acceleration. That means constant throughout the motion. Okay? So it is simply your acceleration A. So what it gives me? V is equal to simply AT. Clear? Okay, now let's look. Okay, since in Newtonian mechanics there is no bound on the velocity, but in special theory of relativity there is a bound on the velocity. Now if you move towards, let's say, if you move for a longer time, what it means? So the velocity will increase. So it can go to the infinity. Clear? So as t tends to infinity, so velocity tends to infinity. That's not true. That's not valid in relativity. Clear? So that means the notion of constant acceleration in the Newtonian mechanics, we have to refine it for the what? for special theory of relativity. Clear? So how we define the uniform acceleration? Clear? Okay, so let me define a uniform acceleration in the special theory of relativity. Everybody has got the idea? So the defining is, in a simple way the constant acceleration, it is not sufficient. Clear? Okay. So let me write the definition. So acceleration is said to be uniform okay in special relativity okay if it has same value in any co-moving frame. Okay? Okay, so what I mean by that, okay, so when you choose the constant acceleration, you are going along a word line, correct? So that word line specifies its co-moving frame. Co-moving frame I have defined last time. So if you are having a particle, if you are having some, a particle that's moving, that's at rest in its own frame of reference, okay? So that frame of reference, you can say it's a co-moving frame, okay? So in other words, the instantaneous rest frame of reference defines your what? Co-moving frame. So, okay, so if you are moving, let's say, along a trajectory, let's say for example, so take this very point, this point, this. So these are all momentarily rest points, momentarily rest. Clear? So the frame of reference that is attached with this object that you call as a co-moving frame. It means so at every instant, each co-moving frame, so it is having the same value everywhere. Okay? So you will see actually it restricts the speed of light. Sorry, it restricts the velocity of body within the limits of the special theory of relativity. Clear? So, Shaman? Got it? Huh? Okay. So let me write. So everybody has got it? Huh? So in each co-moving frame of reference, the acceleration should be same. The value of the acceleration should be same. Okay, if you look here, so at each point you define a velocity, correct? So when you are having a velocity, since the velocity is changing, so if you go from one frame to the another frame, correct? So that should yield you the change in acceleration, because change in velocity gives you the change in, but we are restricting our concern here to a uniform acceleration, okay, or the constant acceleration. It means your acceleration must be what? It should be constant. In other words, it should be same for each co-moving frame. Got it? Okay. So that is at each instant the acceleration in any, since we are dealing with inertial frames, we are not doing any kind of non-inertial frames. So this is very important point. Okay, we will see in a moment the deviation from the inertial frame of reference in a moment. In any inertial frame, traveling with the same velocity. Okay, and the particle has the same. Okay, so this defines our uniform acceleration. Clear? So what I mean by that, suppose you are having some particles accelerating at a constant rate. Okay, and observer is watching that. Clear? So that means, so you can think the observer, let's say stationary observer. Okay, so he measures the acceleration at each instant of time. So what he should get? The same value of the acceleration. It's all. Clear? So this is the simplest of way to think it. Okay. So now let's calculate the trajectory of the particle if it is accelerating. I mean, if it is moving at the constant rate, constant acceleration. Okay, let me give an example of this thing. I mean, constant acceleration. Let's say if you are in a spaceship, clear? So cut off its engines. Okay, so what it will do? So it will be moving at the constant acceleration, uniform acceleration. Take off let's say you are in a lift, clear? So you cut off its engines and forget about the inertia which you feel initially and the at the end. But during that fall, so what you are observing? A constant acceleration, clear? So that's how we define constant acceleration in special theory of relativity, clear? Okay, so now let's look at the trajectory of a particle in a constant uniform acceleration. Now look at the Newton's equations. Okay, so what is the trajectory? So if you look, as you know, ut plus half a at square. It is actually in the uniform acceleration. Acceleration is constant. So what is the nature of the trajectory? It's a parabola. Okay, or in other words, you are having this x is equal to half a. Forget about initial velocity is, let's say, 0. So it is simply at square. It is simply a parabola. You are having a parabolic motion. Let's say locally, you apply the Newton's law of gravity, you throw a particle, it will always follow a parabolic motion. Now let's look from the perspective of the special theory of relativity. Clear? Okay. So it's more to it. And this will, okay, so if you follow this carefully, it will give us actually the resolution of the paradox, the Tune paradox. Clear? Okay. So let's assume, we will constant our motion only along the x direction. We will not consider along the arbitrary direction. Okay? So we will say a particle moves along. Okay? Let's assume a particle moves along x direction with uniform velocity. Sorry, with uniform acceleration. Clear? Okay, so now we are having these relations. In the special theory of relativity, ui is equal to minus c square, and ai that's equal to 0. Clear? So these are the relations. You sure? Okay. So so let's call this as 1. Let's call this as 2. So one more thing, since I am having a uniform acceleration, I have to define now the amount of acceleration. Clear? So if I am having 4 vector acceleration ai, that means ai, it should be something a square. And a is a constant quantity. So what this will give me? It will give me simply the magnitude of square of the magnitude of the quantity a. So what this gives me? Let's say if you are having ds square minus c square dt square plus dx square. So what it gives me? Length of the interval, or the square of the or simply square of the length of the interval. It means it gives me the length of the arc. So length of the arc. So here it will give me simply the magnitude of this acceleration. Clear? So understand this thing. So if you are having any 4 vector, let's say, so ai, so this will always give you the length of that very 4 vector. So that's that a0 square plus a1 square, okay, plus let's say a2 square plus a3 square. So that's your a square. So this will give you the length of the vector. Okay, length of the vector means the magnitude of that. Okay. So a is a constant term here. Now let's rewrite these things. So let's take this very equation. Okay, so I am having equation 1. So I can write, since my motion is only which direction? X direction. So that means velocity along y and z is 0. So I will consider only the 2 components, 0th and 1. So it means I am having, let's say, u0 and u0 plus u1 that's equal to minus c square. Okay, so or I can write it minus u0 square plus u1 square. So that's equal to minus c square. Clear? Okay, so what is u0? It's something, if you see, it's c dx tau, sorry, dt tau by d tau. Okay? So, just we have seen dx by dt is your forward velocity, clear? So the zero component will be t, okay, plus. So what this is? So it is simply your dx of tau by d tau whole square. So that's equal to minus c square. Or you may, yes?
dt, dx by dt.
No, dx by d tau. I am in the forward velocity. Okay, I am simply converting u1 in terms of x and t. I have not changed my tau here. So you can write or minus c square. So let me write simply dt by d tau. So forget about the augment for the time being. So it means it is dependent on tau, clear? Plus dx by d tau whole square equal to minus c square. Let's call this as equation 4. Okay? समझ आओ? Okay, now tell me what can be the possible solution of this very equation? Now it is something, okay, so let me write, it's something minus x square plus y square is equal to some c square, clear? So when this can be whole, so if you know the relation, hyperbolic functions have this kind of property. If I write, let's say if it is x square minus x square plus y square is equal to 1, let's say for example, so you can say it is cos square hyperbolic minus sine square hyperbolic is equal to 1. You know the hyperbolic functions have this kind of identity. It means I can always propose a solution of this equation 4 in terms of the hyperbolic function. Okay, so you can see I am having like this. Okay, so cos hyperbolic square minus sine hyperbolic square x, that is always equal to 1. Okay, so now if you look, it looks like the same thing except these c factors. I need to adjust these c factors. समझ आओ? Okay. So any problem here? Okay. So have you written it? Okay. Shall I proceed? Huh? Okay. So let me write the solution of equation 4 can be written as, okay, so let me write, since the solution is what? dt tau, is it? By d tau. Clear? समझ आओ? So let me write it as something sine hyperbolic, some f of tau. F of tau is unknown to us. You can write sine hyperbolic theta. Okay, so I will write here as a function f of tau, which I need to figure out. Okay, because this t depends on tau. That's why I have put it as a theta of tau. You can put theta of tau, no problem. Okay, so similarly, I can write now dx tau by d tau. So let me write it as c cos hyperbolic f of tau. Now you can check it. So what is the first term? D tau, that contains c minus c square, this objective, plus c square, this objective, is equal to minus c square. Clear? You can take minus out, it will be cos square minus sine square is equal to 1. So it satisfies that very equation. Clear? So let's call these as equation 4. What is unknown to us now? So now I have figured out what the solution is. I can integrate them, figure out what t and x, that will specify my trajectory. But I need to figure out first what? F of tau. Now let's look at the constraint, what we are having at hand. So you are having this objective AI that's equal to what? A square. Clear? Okay. So now let's since my acceleration, now here I am applying my constant acceleration. What it means? So it means a0 plus, okay, a1 that's equal to a square. So what it gives me? So this means, okay, so let me write it, a0 square, okay, plus a1 square, okay, so that's equal to a square. So what it gives me? So minus, so a0 is double derivative of t. Okay, so what is our ai? So ai is simply d2 xi by d tau 2. Clear? So that means a0 will be
C.
c. Okay.
C.
Double derivative of d2 t by
Tau.
d tau. Clear? समझ आया? Okay. Then what will be a1? A1 will be double derivative of x with respect to tau. So that's equal to a square. Now I know the first derivative of t. Okay. So I know the first derivative of t here, is it? So now I need to do, okay, so let me write it like this thing. So it is minus times c d by dt of, okay, d by d tau of that sine hyperbolic, okay, f of tau. Clear? Clear? The first derivative I know by that very solution plus d by d tau of cos hyperbolic c times hyperbolic f of tau whole square is equal to a square. Clear? समझ आओ? Okay, what I have done? So you have using equation. Okay? So now let's differentiate it. So what is the differentiation of sine hyperbolic? It is cos hyperbolic. But there is f. So you have to put the derivative of f as well. Huh? Derivative of f with respect to tau. Similarly, you will be having sine hyperbolic here, derivative of f. Clear? So that means in both the terms you will be having a derivative of f. So that you can take out. Okay? And you will be having c square here, c square here. So समझ आओ? Clear? So what will be this thing? So which gives you, so minus c square derivative of f. Clear? Okay, so what is that? So let me write f prime of tau. F prime of tau means df by dt. Okay, but there will be a square because it was inside the square. So what remains there? So the first term is cos hyperbolic square f of tau. Because in the first term there was a minus sign, I am taking pulling it out. So it will be here simply sine hyperbolic square f of tau. So what that is equal to e square. So this is equal to, so which gives you simply f prime of tau, that's equal to, okay, let me take square. So get what matter? So no. What was the previous thing? Somewhere. So there is, this is cos, huh? Okay. Huh? So we are having a minus issue here, right? Huh? So we are having a minus issue here. So cos gives you sine, is it? Sorry. So cos gives you sine. The first term was cos. So it is sine. So here you get actually, so differentiation of cos is sine, and you are having minus already here. It is sine square hyper f of tau plus cos hyper. So cos square minus sine square is equal to 1. Clear? So it is now equal to a square by c square. What it gives me? So you are having this f dash of tau simply equal to plus minus a by c. So time 10 to, so it will not take much time. We are almost done. Now look here. So what I have taken here, so f dash will be simply plus minus a by c. Clear? So you can absorb this minus into a. You can think, let's say a particle comes from, let's say, some infinity, it comes with some acceleration or it decelerates. So you can assume both kinds of possible motions. So when you are having a deceleration, deceleration of a particle, so it means the acceleration negative. You can also consider that as a uniform acceleration. Clear? So if a particle accelerates uniformly, so you can take that as positive. So in other words, I can absorb this minus in this very case. Clear? So now differentiate, okay, so integrate it. So we can absorb this thing. So we will take only the positive side. So it is simply df by d tau. So that's simply equal to A by C. So now you can choose, okay, so f of tau will be simply equal to A by C tau plus some constant of integration. Okay, now look here. So if you look at this f of tau, it depends on this proper time, clear? So it will this f0 will depend on how you choose the initial time on the clock. So if I choose my initial time on the clock, which is moving with this co-moving frame, so let me choose that equal to 0. So let me start my motion at tau equal to 0, proper time tau equal to 0. So then I can choose this f0 equal to 0. Okay, so it means I am just I mean reorienting my origin of the clock. I mean, so we can always choose this equal to 0. Choose this to be 0. Okay, so what it gives me simply, this f of tau is equal to A tau by C. Now let's look at the solution now. So what is our solution? So everybody has written it? Okay, so therefore, so my dt by d tau, so that's equal to sine hyperbolic A tau by C. Then you are having dx by d tau. So my equation C. So it is something cos. Is it cos?
Sine.
It is sine. Sine hyperbolic A tau by C. So it is C.
Cos.
Really? Yes. It's cos hyperbolic A tau by C. Clear? So now integrate them. After integration, so it will be t is equal to, what is the integration of sine hyperbolic? It will be cosine. Clear? So it will be something t is equal to cosine hyperbolic A tau by C. So here it will be C by E plus some initial time t naught. T naught is actually the coordinate time. Clear? Okay. So what here? So x will be simply equal to, it will be simply c square by a. So c is already here, c will come here. So sine hyperbolic A tau by C plus some x. Okay, so what is now the nature of the trajectory? So this is a parametric form of actually hyperbola, is it? So with the vertex at t is 0, x 0. Correct? So you can write it. So let me rewrite it. So it means you are having p minus t naught, okay, with c square. With the minus sign, let me put here. So it's minus c square like this thing, let's take. So x minus x naught square. So that will be simply, so if I am taking square, so it will be simply c raised for 4 divided by a square. What is this equation? It's an equation of a hyperbola. Is it? So that means the trajectory of a particle which is moving at a uniform velocity, uniform acceleration, it's always a hyperbola. But in Newtonian relativity, Newtonian mechanics, what you are having? A parabola. So this is a very okay. So you can divide it. This c raised of 4 by a square. You divide it here and here. It will be simply x square by a square minus y square by b square is equal to 1. Clear? So that is the equation of hyperbola. So now let's draw. So this is our so this is x and t. These are the coordinates. This is an inertial observer. Okay, so this observer is an inertial observer. Let's say a ground observer who is staying stationary, and another person is accelerating at what? A uniform acceleration. Clear? So he will observe that observer. So what it means? So you can think it this way. Since it's a hyperbola, so if you can, okay. So first put a vertex here. So it is your t. So which point it is? So it is your t naught, and this is your x naught, the coordinate time. So you can say, okay. So now you draw, actually first you draw which line? The line at which the velocity propagates, the null line. Clear? So line of the light cone. So it is something. So let. So you see actually the light. So let's say this is our light cone. Okay. So the lines of light cone. Okay. So this is our light cone. I have told you. I mean, this is like this thing. This light cone. Clear? So it is something okay, like this thing. आवाज समझ? So let me not draw it this way. So everybody got what I am trying to say? Everybody got what I am trying to say? So these are what? So this is a line at which light propagates, and this is the same line. Now what you are having? You are having a uniform acceleration. You can think this observer. So an observer is sitting, let's say here, the stationary observer. He is watching which person who is moving at uniform acceleration. So that observer moves on a hyperbola. Clear? So you can think it in this way. So you can draw a hyperbola like this. So this is one of the possibility. Clear? Depending upon how you choose this. Sorry, this is areas of how you choose the acceleration. So समझ आया? So it means the trajectory will be like always like this thing. समझ आया? So this is an observer. So each observer is having a different acceleration. So let's say it is having A1, A2 and A3. So as much as, okay, if A increases, let's say, so it reaches to which line? So it may reach to this line, this null line. When a person accelerates, the velocity will increase. Clear? It will not increase beyond C. It may reach to C. So what these lines means? You need to understand these lines. These lines mean, suppose if you are having, since I have considered from minus infinity to plus infinity, clear? So it means there is an observer who is accelerating and I am watching that observer. Okay, I am here at the ground and there is a person who is moving at a uniform acceleration. It has come from minus infinity with certain acceleration, then it has decelerated, lowered its acceleration, then gone again to the plus infinity. It means like this thing. So you start from the minus infinity, go to the plus infinity. Clear? And the path is what? A hyperbolic. Okay. So now so let's apply it to our twin paradox. Clear? So we'll do the detailed analysis. So first let's try to do it in a more different way. So now let's take an observer who starts with some acceleration here. Let's say an observer who starts some acceleration here, clear, a motion, and goes through this very trajectory, clear. So this observer will do what? Let's think an observer here is watching that very observer. So these lines you can think, okay, so let me draw these very lines. So like this thing, these are all inertial observers, okay. So these vertical lines means what? An inertial observer who is stationary with respect to this accelerating observer. समझ? You sum very carefully. Now let's do it this way. Suppose I throw a light, I send a light signal to this very accelerating observer. Clear? And let's look, can that observer receive that signal or not? Up to what limit it can receive that very signal. Suppose I am here. Okay? So, okay, let's say I am going along, I am stationary with respect to this very observer, and I am sending a signal like this thing, because the signal should go along this line at the velocity of light. So it is something at a 45 degree, okay, with this vertical line. So that means this observer will receive here. Let's assume. So that means this light signal is being received by this very observer. This will give you an idea of the twin paradox, what is happening. Now let's say you are here. So what will happen? So it may receive it in the finite duration. Clear? Because when you have to understand the time dilation, there will be always a time dilation. Now if you send a signal here, so there will be a finite time dilation. A measurable time dilation will be there, and with a time dilated signal he can receive it. There is a possibility. Clear? Now let's say if you are here, so when you send a signal, so it will go up to the infinity, is it? So that means this observer will receive this signal where? At infinity. What does that mean? So that means he is not able to receive this very signal. This signal has In other words, there is an enormous time dilation between, between an observer here and an observer who is moving where? Who is accelerating. Clear? Samajh? Now, if you are here, so you send a signal. So this signal will never reach to the accelerating observer. Why? Because this accelerating observer cannot go at the velocity of light. Clear? It will reach to the velocity of light, very near to it, but it cannot go beyond this limit. Clear? So in other words, this will make a horizon. So we call it as an event horizon. Huh? So these will be simply the event horizons for this accelerating observer. Okay. Now look at the time dilation effect. So is there an asymmetry in this time dilation? Do you think there is an asymmetry? So you are okay, if you are having both the let's assume both the observers are inertial. You can say one is moving with respect to the another and another say it's moving with respect to the another. Clear? A is moving with respect to B, B is moving with respect to the A with the same effect. Clear? But here the acceleration breaks this very symmetry. Do you think so? Huh? So acceleration produces actually an enormous time dilation effect, okay, which is not reciprocal in nature. So that means this very observer will always see how much? An enormous time dilation. In other words, an observer who is moving at a constant acceleration with respect to an inertial observer will always look what? Less in age than an observer who is sitting where? On the ground. समझ आओ?
Sir, the stationary one, sir, the light signal that he is sending, उसकी velocity पे भी depend करता है.
नहीं, उसकी so what I am saying, I am trying to look at that very observer. I am trying to look at this very observer where he goes. I mean, is he able to receive my signal or not? So when he is not able to receive my signal, what does that mean? There is an enormous time dilation. So you can think it this way. So this sends a signal to this very observer, he sends it back. Okay, so that means you are able to receive it all the way you are trying to connect it. But at certain point of time, you are not able to connect it. What does that mean? So there is a time dilation of which observer? Who is in accelerating frame of reference? Clear? So in other words, when you are having a time dilation, what does that mean? The clock of that observer slows down.